And finally, we're here to section 9.4, the section we've all been waiting for. Uh, how to solve systems of differential equations when A is non-defective. Okay, in other words, it's diagonalizable. So let's look at x prime equals ax, where A is a diagonal matrix. Okay, so 5, -3, 10 along the diagonal, zeros otherwise. Okay, if we were looking to solve the system of differential equations for this, what would it look like? Well, x1 prime would equal 5 times x1 plus 0 times x2 plus 0 times x3. In other words, you'd have the first equation being x1 prime, the derivative of an unknown function is 5 times itself. X2 prime would look like 0 times x1, -3 times x2, 0 times x3. So that would look like x2 prime equals, the derivative of x2 is equal to -3 times itself, and x3, the derivative of that would be 10 times, the derivative of x3 would be 10 times itself. Okay, well, what you see here is each one of the derivatives, x1 prime, x2 prime, and x3 prime, depends on x1 and x2 and x3 respectively without depending on any of the other functions. So it's like solving three independent differential equation problems. Okay, so since the derivative of x1 depends on only on itself, you can say what function has derivative 5 times itself. That's easy. C1 e to the 5t. Same with x2 prime, same with x3 prime. And this is made easy by the fact that we're working with a diagonal matrix. It's not like x1 prime has anything to do with x2 or x3. Same with x2 prime, same with x3 prime. Okay, so in general, whenever you're working with a diagonal matrix A, where you have lambda 1, lambda 2, all the way down to lambda n across the diagonal and zeros otherwise, the solution to that system of differential equations will look like x1 is the function c1 e to the lambda 1t, x2 is the function c2 e to the lambda 2t, and so on. So this is simple when A is a diagonal matrix, but what if A isn't? The answer is to diagonalize it. Okay? So why does that work? Okay, if x prime is equal to ax, where A is diagonalizable, because remember this section, it's for non-defective matrices, then we know that A can be written in terms of D and S, where D is the eigenvalues to A and S is the eigenvectors to A. S inverse happens to be the inverse to S. Okay, such that D equals S inverse AS. Now, if we solved for A, we could say that A is equal to SD S inverse. So sub that in right here into this differential, or this vector differential equation. What you get is x prime equals SD S inverse times x. Okay, if you multiply on the left by S inverse, you get S inverse x prime equals D times S inverse x. Now the trick here is to define y to be the matrix S inverse times x. Okay, x is really the unknown here that we're looking for to solve this system. Okay, let y be S inverse x. What's y prime? Okay, well, if y is S inverse x, then y prime ends up being S inverse x prime. It takes some time to show that, but it's true. So we can reduce this differential, or this equation right here, to y prime equals dy, where d was what? Well, d was a diagonal matrix. Okay, so if d is now a diagonal matrix, then this system right here, y prime equals dy, has this as its solution. That was just discovered on the previous page 3 minutes ago. Okay, so that means since y is S inverse x, that means S inverse x is equal to that. And if S inverse x is equal to this, then x, if you multiply by S on both sides, is equal to the n by n matrix of eigenvectors of A times C1 e to the lambda 1t, C2 e to the lambda 2t, Cn e to the lambda nt. Okay? So if you take the matrix S that has column vectors that are the eigenvectors to A, and you multiply it by this, you get the general solution to be C1 V1 e to the lambda 1t, C2 V2 e to the lambda 2t, Cn Vn e to the lambda nt. Okay. Now, way back when we started this, can't find my notes, we were tasked with solving this system of differential equations. Okay, and I told you what the answer was. Suppose I didn't tell you what the answer was. Suppose I said, we're going to solve this. What would you do? Well, we get to try it now. Okay, first off, we convert this to x prime equals a 4, 2, negative 1, 1 times x. Okay, and that's x1 prime, and that's x right there. Sorry about that. Okay, this is not a diagonal matrix. So we need to make it a diagonal matrix. So that means we need to diagonalize this. So that means we need the eigenvalues to 4, 2, negative 1, 1, and the eigenvectors. Okay. So let's put this aside and find the eigenvalues. We need to take the determinant of A minus lambda I. So that's the determinant of 4 minus lambda, 1 minus lambda, 2 and negative 1. So 4 minus lambda times 1 minus lambda minus a negative 2 is equal to 0. That's lambda squared. We get minus 4 lambda minus 1 lambda, that's minus 5 lambda, plus 4, plus 2 is equal to 0. So that's lambda squared minus 5 lambda plus 6 is equal to 0. So lambda equals 3 and lambda equals 2 are the eigenvalues. Now each one of them will have a corresponding eigenvector. So for lambda equals 3, that means A minus lambda I looks like 4 minus 3, which is 1, 2, negative 1. 1 minus 3 is negative 2. That row reduces to 1, 2, 0, 0. So x2 is a free variable, say it's equal to itself. x1 is equal to negative 2 x2. So the vector x1, x2 is equal to x2 times negative 2 and 1. So negative 2 and 1. Okay, and lambda equals 2. So these are the eigenvalues. These are the eigenvectors. For lambda equals 2, what's this? 4 minus 2, that's 2, that's 2, that's negative 1. 1 minus 2 is negative 1. So this row reduces to 1, 1, 0, 0. So x2 is free. x1 is equal to negative x2. So the vector x1, x2 is equal to x2 times the vector negative 1, 1. All right. So, putting this all together. Okay. The solution looks like C1 V1 e to the lambda 1t plus C2 V2 e to the lambda 2t. Okay, so we'll call this eigenvector eigenvalue 1, eigenvector eigenvalue 2. So the solution here to x prime equals ax looks like C1 times the vector, make sure this is showing up. There we go. C1 times the vector negative 2, 1 times e to the 3t plus C2 vector 2, that's negative 1, 1, times e to the lambda 2t, so that's e to the 2t. Eigenvector 1, eigenvalue 1, eigenvector 2, eigenvalue 2. Okay. This is, I'm going to do baby steps right here. Negative 2 e to the 3t, e to the 3t, plus C2, negative e to the 2t, e to the 2t. Okay, why am I doing that? Because I'm showing you, one sec, I need to find it first. This statement right here, okay, we will show that the system has vector functions, x1, negative 2 e to the 3t, e to the 3t, x2 equals negative 2t, e to the 2t. This is from section 9.3's notes. Okay. I don't know that it's all on the same screen. Yeah, it is. Okay. So negative 2 e to the 3t, e to the 3t, negative e to the 2t, e to the 2t. Okay. So the theorem in that we learned in section 9.3 says the general solution is constant 1 times vector 1 plus constant 2 times vector 2. So combine all of that. You get minus 2 c1 e to the 3t minus c2 e to the 2t, c1 e to the 3t plus c2 e to the 2t. Okay, and the first row here is the unknown function x1 that solves the differential equation. The second row there is the unknown x2 function that solves the differential equation. So, sorry, I'm kind of fumbling around. There we go. So in other words, to solve the system of differential equations, x1 prime is 4 times x1 plus 2 times x2, and x2 prime is negative x1 plus x2. Okay, the solution to that is found right there. And how did we find it? By diagonalizing the matrix A. Okay, we found its eigenvalues and eigenvectors. Okay, we found those to be right here. And then we looked at a linear combination of eigenvector 1, e to the eigenvalue 1, plus eigenvector, C scalar times eigenvector 2, e to the eigenvalue 2. And if there were more eigenvector and eigenvalues, we would do the same exact thing. Okay, so let's look at one where there's more. Let's try this. So we just did this problem. x1 prime is negative x1 times 2x2 plus 2x3. x2 prime is 2x1, 2x2, 2x3, and so on. Okay. So I need to find something to write on. This will work. Let's write the vector differential equation we're looking to solve. X prime is equal to negative 1, 2, 2, 2, 2, 2, negative 3, negative 6, negative 6 times x. Okay, we need to diagonalize. Okay, so that's negative 1 minus lambda, 2 minus lambda, and minus 6 minus lambda, 2, 2, 2, 2, negative 3, negative 6. All right. So hopefully this determinant isn't totally awful. We'll expand across the top row. So it's minus 1 minus lambda times 2 minus lambda, 2, negative 6 minus lambda, minus 2 times. Cross out the row and column, we're at 2, 2, negative 3, minus 6 minus lambda. Cross out the row and column. Up top, we're at 2, 2 minus lambda. Oops, sorry. 2, 2 minus lambda, negative 3, and negative 6. All right, see what this boils down to. Minus 1 minus lambda times 2 minus lambda times minus 6 minus lambda minus a negative, so that's plus 12. Minus 2 times 2 times minus 6 minus lambda minus a negative, so it's plus 6 plus 2 times 2 times, that's negative 12, minus a negative, so it's plus 3 times 2 minus lambda. Okay, let's simplify everything that's in the parentheses first. This is minus 12 plus 6 minus 3 lambda. So that's minus 6 minus 3 lambda. What's this? This is minus 12 minus 2 lambda plus 6 minus 12 minus 2 lambda plus 6. So this is minus 6 minus 2 lambda. And what's going on here? This is lambda squared minus 2 lambda plus 6 lambda. So that's plus 4 lambda. And this is minus 12 plus 12. So that's minus 1 minus lambda times that cancels out. We get lambda squared plus 4 lambda. Make sure I did this right. Negative 12. So it's minus 6 minus 3 lambda. It's plus 3 lambda. All right. Minus 6 minus 2 lambda. And that's going to be multiplied by, minus 2 times minus 6 minus 2 lambda plus 2 times minus 6 minus 3 lambda. So this ends up being, what, 12 plus 4 lambda. This is minus 12 minus 6 lambda. What does this end up being? I'm just checking my arithmetic right here, making sure that everything's fine. I was expecting those to zero out, but maybe they don't. 2, negative 6 minus lambda, negative 3, 2. All right, let's just keep going. Negative lambda squared minus 4 lambda minus lambda cubed minus 4 lambda squared. When you distribute the negative 1 and the negative lambda through there, add it to the 12 minus 4 lambda, 12 plus 4 lambda, and minus 12 minus 6 lambda. So these things are going to cancel out. We have a minus lambda cubed right here, minus lambda squared, minus 4 lambda squared, that's minus 5 lambda squared. And then we have a minus 4 lambda, a plus 4 lambda, well, those cancel each other out, minus 6 lambda. All right, and this is all going to be set equal to 0. Fear not, this looks very solvable. You can factor out a negative lambda. You get lambda squared plus 5 lambda plus 6 equals 0. So this is minus lambda times lambda minus 3 plus 3, lambda plus 2. Does that all look right? Yep. So so lambda equals 0, lambda equals negative 3, and lambda equals negative 2 are our eigenvalues. Holy smokes. That was a lot more. Now, we have to find the corresponding eigenvector for each of these. Okay, so we'll put the eigenvectors underneath. Once we find those, the problem will almost be over. So if lambda is equal to 0, okay, so the case where lambda equals 0, what's a minus lambda I? Well, it's minus 1, 2, 2, 2, 2, 2, and negative 3, negative 6, negative 6. All right. So it looks like row 3 is a scalar multiple. Oop, no, it's not. Negative 3, negative 6, 6, negative 1, 2, 2. It's not. All right. So let's multiply row 1 by 3 and add it to row 3. So, or subtract it, I guess. Here, let's do this. 1, negative 2, negative 2, 1, 1, 1, and divide this by negative 3, I get 1, 2, 2. There we go. That's better. Now let's see what I do. Subtract. 1 minus 1 is 0, minus 2 is minus 4, minus 2 is minus 4. It's 1, negative 2, negative 2. 1 minus 1 is 0, negative 2 minus 1 is negative 3. Negative 2 minus 1 is negative 3. All right, row 2 and row 3 are scalar multiples of 0, 1, 1. So that's 0, 0, 0 on the bottom. That's 1, negative 2 on top. Let's take this one step further and let's multiply row 2 now by 2 and add row 1. So 0, 1, 1, 0, 0, 0. 2 times 1 is 2. So we get 1, 0, 0. All right. So what does that tell us? It tells us that x1 is 0. It tells us that x2 is equal to negative x3, and x3 is equal to itself. So this is equal to x3 times the vector 0, negative 1, 1. So let's write that here. 0, negative 1, and 1. All right. What happens if lambda is equal to 3? If lambda is equal to 3, then we have negative 3. Minus 1 plus 3, that's 2. 2, 2, 2. 2. 2 plus 3 is 5. 2. And minus 3, minus 6. Negative 6 plus 3 is negative 3. This is a negative 3. So that's 1, 1, 1, 2, 5, 2, 1, 2, 1. And now we row reduce. So 1 minus 1 is 0. 1 minus 2 is negative 1. 1 minus 1 is 0. That's 1, 1, 1 still. If I multiply row 1 by 2, I get 2 minus 2 is 0. 2 minus 5 is negative 3. 2 minus 2 is 0. So now this is the matrix 1, 1, 1. 0, 1, 0, 0, 0, 0. So, one more step. 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 0 is 1. 0, 1, 0, 0, 0, 0. And we get x1, x2, x3 is equal to so x3 is free, x2 is equal to 0, and x1 is equal to negative x3. So this is x3 times negative 1, 0, 1. Negative 1, 0, 1. Sorry about the length of this. If I had known that the problem was as long as it was, probably would have just jumped to what the solutions were for this, but you're at least getting a little bit of a review on this. All right, so next, lambda equals negative 2, if my memory serves me right. So if lambda is equal to negative 2, I get minus 1 plus 2. Minus 1 plus 2 is 1. 2, 2, 2. 2 plus 2 is 4. 2, minus 3, minus 6. Negative 6 plus 2 is negative 4. So hopefully this is all right. Looks good so far. Let's scale this real quick. 1, 2, 2. 1, 2, 1. Negative 3, negative 6, negative 4. All right, let's multiply row 1 by 3 and add. So that's 3 plus negative 3 is 0. 6 plus negative 6 is 0. And 6 plus negative 4 is 2. And let's subtract row 1 and row 2. So 1 minus 1 is 0. 2 minus 2 is 0. 2 minus 1 is 1. All right. This is easy. 1, 2, 2, 0, 0, 1, 0, 0, 0. So let's multiply row 2 by 2 and subtract. And that's what you get. So x1, x2, x3 is equal to, let's see, x3, there's a pivot there, there's a pivot there, so x2 is the free variable, x3 is equal to 0, and x1 is equal to minus 2x2. So this is equal to x2 times negative 2, 1, 0. Negative 2, 1, 0. All right. 3 eigenvalues, 3 eigenvectors. Our general solution, x of t, is going to be of the form c1 times vector 1. So that's 0, negative 1, 1 times e to the 0t plus c2 vector 2, negative 1, 0, 1, e to the negative 3t plus c3 vector 3, e to the negative 2t. Combine all of that together. E to the 0t, that's just what? 1. So c1 times 0, that's 0. That's 1, so that's minus c1. That's c1. Plus minus c2 e to the negative 3t. 0 times c2, that's 0. 1 c2, so that's c2 e to the negative 3t. This is minus 2 c3 e to the negative 2t plus c3 e to the negative 2t plus 0 times c3, 0. So reading this straight across, unknown function number 1 is minus c2 e to the negative 3t minus 2 c3 e to the negative 2t. Function number 2 is minus c1 plus c3 e to the negative 2t, and x3 is c1 plus c2 e to the negative 3t plus 0. All right. The answer doesn't look pretty, but these 3 functions, x1, x2, and x3, are the functions that will solve this system of differential equations. Okay. I can't really organize it in any way where you can see them both on the same screen, I don't think. Anyway, this function 1, x1 being negative 2c2 e to the negative 3t minus 2c3 e to the negative 2t, c2 negative c1 plus c3 e to the negative 2t, and x3 being c1 plus c2 e to the negative 3t solves that system of differential equations. All right, so that's what you do when the matrix A is diagonalizable. Okay, in the 2 by 2 case and in the 3 by 3 case. And all the problems are going to look like either this or this for section 9.4. The next thing you have to ask yourself is what happens if the matrix A is defective or it's not diagonalizable, and that's what comes in section 9.5. Okay, so take care. Hope you're having a great one, and I'll see you next time.